I'm Bahruz Jabiyev from Northeastern University in Boston. Welcome to Boston, everybody. Today I'll be telling you about the security implications of HTTP2 to HTTP1 conversion anomalies. So when we open up our browsers and use the internet, our browsers used to generate HTTP1 requests like the one we see here. This request essentially sends the query of funny cats to the search endpoint of google.com. However, it's not the case anymore. HTTP1 has already given its place to HTTP2 because it solves major problems of H1, including head-of-line blocking and repeating header names and values. In HTTP2, we could convey the same request in multiple frames. Here in this example, we have 3 frames. The first one is a headers frame. Headers frame contains headers like the path and the host name. The next frame is a continuation frame, and it continues with some additional headers, like the content length header and the user agent header. And headers flag says that there will be no more headers in this stream. Finally, the data frame essentially carries the request body, which is funny cats in this example. An end stream flag is saying that this is the last frame in this stream. So when users send HTTP2 requests to their endpoints, they usually hit reverse proxies. Reverse proxies are very common on the internet in the form of load balancer, cache servers, CDN servers. And when reverse proxies receive HTTP2 requests, they convert them into an HTTP1 request before forwarding them. This conversion is happening mainly because of the compatibility and performance reasons. And when we looked at 10 popular reverse proxies, including CDN servers, we saw that 9 of them had no support for speaking HTTP2 to the upstream. And later in our experiments, we saw that every single reverse proxy we tested, you send HTTP1 request to the upstream. All of this says that HTTP2 to HTTP1 conversion is very common on the internet. The goal of this research is to investigate the anomalies in this conversion process and their security implications. So past research has looked at conversion anomalies only in the context of request smuggling. Past research has also shown request body parsing to be at the root of many severe recent HTTP attacks. Therefore, in this research, we focus only on the body-related conversion anomalies, and however, we do not constrain ourselves to any specific type of attack or anomaly. We developed an HTTP2 fuzzer to conduct this research. The name of this fuzzer is derived from a biological concept. When we developed the mutation approach for this fuzzer, we took a lot of inspiration from the way DNA sequences are mutated in living cells, especially the frameshift mutations. Therefore, we called this tool FRAMESHIFTER. As a first step, FRAMESHIFT generates an HTTP2 input from a user-specified grammar. And grammar essentially defines what a frame sequence can look like, or what the individual frames will contain, or what are the individual elements of the individual frames. Once the input is generated, mutations are applied. There are 2 types of mutations: sequence mutations and content mutations. In content mutations, we essentially add, replace, or remove random characters. And once it's another mutation type is a sequence mutation, where we can add random frames into the sequence. We can drop a frame or we can replace it. We use this tool to conduct experiments. In experiments, to each reverse proxy we test, we send large amount of mutated HTTP2 requests. And for each HTTP2 request we send, we capture the HTTP1 request forwarded by the reverse proxy. We test popular in-house reverse proxies. In addition, we also test popular CDN servers. Once we capture all the forwarded HTTP1 requests by the reverse proxies, we search for the anomalies. To see some examples for some of the anomalies here, Here we have a content length header value bigger than the request body size. This example has a content length header with non-numeric value. Here we have two content length headers with differing values. Finally, here we have a transfer encoding header with double chunked. All of these are direct violation of HTTP RFC. When we draw the picture of what reverse proxies are affected by what anomalies, we see that significant portion of reverse proxies are affected by multiple anomalies. In the paper, we also give details about what input patterns create those anomalies. Once we find the anomalies, for each anomaly type, we come up with attack scenarios. And we test these attack scenarios on server pairs. The first attack we find is denial of service. In this type of denial of service attack, the attacker's goal is to exhaust the connection pool between the reverse proxy and origin. The connection pool is a limited set of connections that can be opened by the reverse proxy toward the origin. And it is shared across all the users, regardless of their source, IP, and locality. So attacker sends a specific malicious HTTP2 input. And when it gets the reverse proxy creates this HTTP1 request, where the content length header value does not match the request body size. It gets forwarded to the origin. And as this request is incomplete, neither reverse proxy nor the origin closes the connection. Therefore, this connection stays open. When attacker sends the same input, the same thing happens, and another connection gets allocated. If attacker keeps doing the same thing, he can easily exhaust the connection pool. What happens as a result, when a victim user comes along and makes a normal request, his request is not served because the reverse proxy is overloaded. The second attack we find is what we call request blackholing. Here, attacker sends a malicious HTTP2 input to the reverse proxy. When it gets the reverse proxy generates this incomplete request and sends it to the origin. As this request is not complete, it'll stay in the request buffer of the origin server. And when a victim user comes along and makes a normal request, reverse proxy will make a normal conversion. However, it will use the same connection to forward that request. As a result, origin will think that the second request is the continuation of the first one and will consume some part of it. And we'll be left with an incomplete request, get confused, and send an error response back. As a result, the victim user gets an error response to its normal request. Attacker can send this type of requests as many times as he wants and affect the user's experience, many users' internet experience randomly. In addition to anomaly-caused attacks, we also find some attacks which are not necessarily due to conversion anomaly. One of them is query of death. What happens here is attacker sends a malicious HTTP2 input, and when it gets the reverse proxy, after this request is processed, reverse proxy dies and stops operating indefinitely. The next attack we find is request smuggling. Their attacker's goal is to smuggle a request into the connection between the reverse proxy and origin. So he sends his request. When it gets to the reverse proxy creates this HTTP1 request, which has another request as in its request body. When it is forwarded to the origin, assuming that GET requests do not have request bodies, therefore parses just the headers block out, and the request body is remaining in the buffer, and request smuggling happens. As you might know, request smuggling can pave the way for many other severe HTTP attacks. When we draw the picture of what server pairs are affected by what attacks, we see that many server pairs are affected by anomaly-caused attacks. And the picture is similar for the additional attacks we find, we see that significant number of server pairs are affected by those attacks. When we disclose these findings to the vendors, Golang, who is the owner of the Caddy HTTP parsing library, assigns a CVE for the query of death attack. Apache Traffic Server also assigns a CVE for all the attacks and findings we report. Varnish confirms our finding. Envoy proxy agrees that there's a gap in their denial of service protection. And finally, Akamai starts a remediation effort under the guidance of one of the authors. In conclusion, we develop an open source and HTTP2 fuzzer. We come up with a holistic and systematic approach to study the conversion anomalies. And we find novel attack vectors. And finally, we work with vendors to reproduce and fix the issues. Thank you. If you have any questions, I can get them.